I skipped the server creation tutorial before as I felt it left the domain of codename 1 too much and ventured into server programming. In this level, we don't skip such things, so I'm going to review the server code related to the restaurant app and why it was built like that. I find server code to be boring. That's not a bad thing. Boring can be great when you need something you can rely on, which is exactly what a good server should be. I'll try to focus on the interesting pieces only, and I won't mention some of the entities or their relationships as they are just more of the same. There are some great Java EE and Spring Boot courses out there, and I don't think it's our place to displace them. Because we did the client first, and the server portion is mostly filling in the blanks, there are still some hidden complex nuggets, but it's mostly simple. Security is one of the more challenging things about server programming. I'll try to explain as much as I can, but once you go into security, there is always more to know. It's a specialty in its own right. Our starting point will be the same Spring Boot project I did in the base course. I'll use MySQL again and create a blank database. We'll use app backend server as the project name. The same database and project will be used for the app maker as well as the app itself. There are some nuances in Spring, such as service components, which are similar to session beans in Java. I'm not using any of those things which would make sense in an architectural standpoint, but aren't really useful for our narrow use case. Let's start right away. Assuming the project was created, adding Braintree support to the server side starts with editing the POM file with the right dependency. This will allow us to compile the code that supports Braintree. The Braintree service is pretty simple. It maps to the Braintree URL. The first thing we do is provide access to the Braintree Gateway. Notice that the normal Braintree API hard codes all of these values, but we load them dynamically and then place them in a cache for reuse. The reason for this is that the Braintree credentials are specific to restaurant, and we will have multiple restaurants running on a single server. The service methods themselves are pretty trivial. The token is generated using the standard Braintree API. There isn't much here. It just returns the string which we use in the client-side code. The interesting method is the purchase method, where we create a purchase request and finally fill in the amount we want to pay. This isn't obvious from the code here, but we have a small security issue in this code. Right here, calculate amount runs on the order, which we received from the client. This means that the prices of the elements in the order were also received from the client. Our client is theoretically trustworthy, but if someone reverse engineers the communication protocol or the client, they could just change the prices of the dishes to give themselves a discount. However, if we just take the dish ID and calculate the price on the server, this will make no difference. This doesn't even have to be malicious. If a price was updated and a local copy of the app still has the old price because the user hasn't launched the app in a year, it's important to make these calculations in the server always. In the final version of the server, this is fixed, but I kept it for now in the interest of simplicity and also to demonstrate how nuanced security issues can be. This is the basic restaurant entity. It allows us to save the details we need of the restaurant. We'll add a lot more into this class, but for now, all we need are these things. Notice that instead of using a numeric auto-generated ID, I chose to use a string, which I've set to a universal unique identifier in the constructor. Numeric IDs are sometimes problematic, as one can potentially guess the ID and scan your database. For example, if someone notices that we have an API called list dishes that accepts the restaurant ID, this might be a problem. He could scrape the API for all the dishes of all the restaurants by scanning integer values. Scanning your universal unique identifier values will take centuries or even eons. When looking at the code, you will see some duplication. In this example, we can see the order entity next to the order data access object, or DAO. You will notice that these values are very similar to one another. A DAO transfers data from the client or within the server, and an entity stores the data. There are often mirror images of one another, but not always. In this case, we can see that the DAO contains things that aren't part of the order. Also, the architecture is different since the entity needs to map to storage structure and the DAO is designed for our convenience. This is a common practice that saves the need to pass entities around and break the separation of the tiers within the application. It allows us to have some flexibility with our data. The versioning service allows us to detect if a new version of the app is available and effectively allows us to disable outdated versions. This is important as we might be stuck with an out-of-date protocol that we wish to retire. We might need to change the server address. Thanks for watching. I hope you found this informative.